this ordinary grain of sand, and the processor inside your computer are fundamentally the same thing. But to transform one into the other, humanity had to build the cleanest, most expensive, and most complex factories in human history. We are about to go inside these massive nano-factories to witness alchemy on an atomic scale. This isn't just about making computer chips. This is the story of how we build the brains of the modern world. Every single piece of advanced technology, from your phone, to your car, to the AI revolution, to the satellites in orbit, relies on this one almost supernatural process. It's a process so demanding that a single speck of dust can be a catastrophe, and so precise. It makes watchmaking look like playing with toy blocks. So, how do we turn a common rock into a thinking machine? The journey is more unbelievable than you can imagine. And it begins with a quest for absolute purity. The entire journey starts by taking sand, specifically quartz sand, which is rich in silicon dioxide, and purifying it to an almost impossible degree. The goal isn't just to get silicon. It's to create something called electronic-grade silicon, or EGS. This material must be 99.9999999% pure. That's 9 nines of purity. A standard so high, it's difficult to even comprehend. Why this insane obsession with purity? Because a microchip is an electrical device built on a perfect, repeating crystal structure of silicon atoms. A single foreign atom, a tiny speck of boron or aluminum, acts like a boulder in the middle of a superhighway. It disrupts the crystal lattice and catastrophically alters the flow of electrons, rendering a potential billion-dollar section of silicon utterly useless. In the world of nanoelectronics, purity isn't a preference. It is the absolute foundation upon which everything else is built. The process is a multi-stage industrial epic. First, the quartz sand is thrown into a colossal electric arc furnace with carbon, heated to over 2,000 degrees Celsius. This rips the oxygen atoms away, leaving behind metallurgical-grade silicon, which is about 99% pure. Impressive, but for our purposes, it's still hopelessly dirty. This raw silicon is then ground into a powder and put into a fluid bed reactor, where it's treated with hydrogen chloride gas. This creates a volatile liquid called trichlorosilane, which is then painstakingly distilled over and over, much like a fine whiskey, to remove all impurities. Finally, this ultra-pure gas is deposited onto heated silicon rods, growing into large, gray chunks of polysilicon, the 9 nines pure material we need. But it's still not ready. The atoms are arranged randomly. We need a perfect, single crystal. This is achieved through the Czochralski process. The polysilicon is melted in a quartz crucible. A tiny, perfect seed crystal of silicon, is lowered into the molten bath, and then slowly, painstakingly pulled upwards, while rotating. As it rises, the molten silicon solidifies around the seed, copying its perfect atomic structure. Over days, a massive, flawless, single crystal cylinder emerges from the crucible. This is the silicon ingot, a dark, perfectly cylindrical monolith, worth hundreds of thousands of dollars, ready to become the canvas for digital masterpieces. But this perfect, black mirror is still just a massive block of raw material. To build circuits on it, we need to slice it into the foundation of every chip on Earth, the silicon wafer. And this requires a level of flatness that defies belief. This ingot, which can be over 6 feet long and weigh nearly 1,000 pounds, is sliced into incredibly thin discs. These are silicon wafers, typically 300 millimeters, or 12 inches in diameter. Each wafer is less than a millimeter thick. They are the substrate, the canvas, upon which hundreds, sometimes thousands, of individual microchips will be born simultaneously. The surface of this wafer must be flawlessly, unimaginably smooth. The features we're about to build on it are measured in nanometers, billions of a meter. A transistor gate can be just a few dozen atoms thick. Any bump, any scratch, any variation on the wafer's surface would be like trying to build a skyscraper on a mountain range. It's impossible. The process of photolithography, which we'll see next, uses light with an incredibly shallow depth of field. If the surface isn't perfectly flat, the circuit pattern will be out of focus and completely ruined. To achieve this, the ingot is first ground into a perfect cylinder, often with a flat notch cut into one side, to help machines orient it later. Then, a hair-thin, diamond-tipped wire saw cuts through the ingot, slicing off one wafer at a time, in a process that takes hours. But this initial cut is still far too rough. The wafers then undergo a series of punishing procedures. They are ground down, their edges are rounded, and then they are lapped between two massive rotating plates with an abrasive slurry. The final, critical step is chemical mechanical polishing, or CMP. The wafer is pressed against a rotating polishing pad, while a carefully engineered chemical slurry washes over it. This slurry both chemically reacts with the silicon and physically abrades it. The result is a surface so perfectly smooth, it's one of the flathead objects ever created by humanity. To put it in perspective, if a 300 millimeters silicon wafer were scaled up to the size of North America, the largest bump on its surface would be less than 2 inches high. We now have the perfect canvas. But how do you draw a circuit with billions of components, each one smaller than a virus? You can't use a pen. You have to use the most advanced and expensive machines ever built In a room cleaner than any place on Earth, you have to use light itself. Single crystal. This is achieved through the Czochralski process. The polysilicon is melted in a quartz crucible. A tiny, perfect seed crystal of silicon is lowered into the molten bath, and then slowly, painstakingly pulled upwards, while rotating. As it rises, the molten silicon solidifies around the seed, copying its perfect atomic structure. Over days, a massive, flawless, single crystal cylinder emerges from the crucible. This is the silicon ingot, a dark, perfectly cylindrical monolith, worth hundreds of thousands of dollars, ready to become the canvas for digital masterpieces. This is where we enter the heart of the Nano-Factory, the clean room. And the core process that happens here is called photolithography. In simple terms, it's like a hyper-advanced form of photography, using light to project a circuit pattern onto the silicon wafer, layer by agonizing layer. This is where Moore's law, the observation that the number of transistors on a chip doubles approximately every 2 years, is made reality. The cleanroom environment is non-negotiable. At the nanoscale, our world is a horrifyingly dirty place. A single human skin cell is a city-destroying asteroid. The air in a typical city office has up to 1 million dust particles per cubic foot. A top-tier semiconductor cleanroom allows for fewer than 1 particle. That's why workers are shrouded head to toe in bunny suits, and air is filtered relentlessly. Without this, the yield, the percentage of working chips on a wafer, would plummet to 0. Photolithography itself is the defining step, because the wavelength of light you use determines the smallest feature you can print. Smaller features mean more transistors, and more transistors mean more power, speed, and efficiency. The photolithography dance has several key steps, and it will be repeated dozens, sometimes over 100 times. First, the polished wafer is heated in an oven containing oxygen, growing a flawless, insulating layer of silicon dioxide across its surface. Second, the wafer is coated with a light-sensitive chemical called a photoresist. It's spun at thousands of RPM to spread the resist into a perfectly uniform layer, just nanometers thick. Third, and this is the multi-billion-dollar step, the wafer enters the lithography machine. These machines, especially those made by the Dutch company ASML, are the largest, most complex, and most expensive manufacturing tools on the planet. Inside, a beam of light is shown through a photomask, which is a master blueprint of one layer of the chip's circuit, etched onto a piece of quartz. For decades, we used deep ultraviolet light. But to create today's most advanced chips, we needed something more extreme. Extreme ultraviolet, or EUV, light. EUV is so energetic, it's absorbed by everything, including air and even glass lenses. So, the inside of an EUV machine is a near-perfect vacuum. And instead of lenses, it uses the most complex mirrors ever constructed. Made by Zeiss, these mirrors are so smooth that if you scaled one to the size of Germany, the highest bump would be less than 1/10 of a millimeter. A powerful laser blasts a microscopic droplet of molten tin 50,000 times a second, creating a plasma that emits the EUV light. This light is then bounced off the complex mirrors, through the photomask, and onto the photoresist-coated wafer, exposing a precise pattern. The machine then steps across the wafer, stamping this pattern hundreds of times. Finally, the wafer is bathed in a developing chemical. This washes away the exposed photoresist, leaving behind a perfect stencil of the circuit pattern. Ready for the next brutal step: molecular surgery. Worth hundreds of thousands of dollars. Ready to become the canvas for digital masterpieces. We've created a stencil. But a stencil isn't a switch. It's just a pattern on the surface. Now, we have to permanently carve this design into the silicon itself, and then surgically alter its atomic properties to bring billions of transistors to life. The next two crucial processes are etching and doping. Etching is the process of using that photoresist stencil to physically remove material. Doping is the process of intentionally introducing impurities into the silicon crystal lattice to change how it conducts electricity. This is how we actually build a transistor, the fundamental building block of all digital logic. A transistor is simply a tiny, microscopic switch. Etching carves out the physical shapes of these components. Doping creates the N-type and P-type silicon regions that allow the gate to control the flow. Without etching, there's no structure. Without doping, the structure can't function as an electrical switch. This is where the blueprint becomes a working machine for etching. Modern fabrication plants use plasma etching. The wafer is placed in a vacuum chamber, which is then filled with a specific gas mixture. A powerful electromagnetic field is applied, stripping electrons from the gas atoms and creating a soup of reactive ions called plasma. This plasma is then directed down onto the wafer. It violently bombards the surface, but only where the photoresist has been removed. It acts like a nanoscale sandblaster, precisely vaporizing the silicon dioxide, carving out the circuit design with vertical, perfectly straight walls. After etching, the remaining photoresist is stripped away. Now, we have the physical structure, but it's all just silicon. We need to dope it. This is done through a process called ion implantation. The wafer is again placed in a vacuum chamber and an ion beam, essentially a particle accelerator, fires a stream of impurity atoms like phosphorus or boron directly at it. This subatomic machine gun embeds these dopant atoms into the exposed silicon, changing its electrical character in those specific regions. This creates the different parts of the transistor that allow it to switch on and off. This light is then bounced off the complex mirrors, through the photomask, and onto the photoresist-coated wafer, exposing a precise pattern. The machine then steps across the wafer, stamping this pattern hundreds of times. We have now built a single layer of working transistors, billions of them sitting on a wafer. But a processor isn't a single-story building. It's a sprawling, three-dimensional megacity with over 100 floors. Now comes the monumental task of wiring it all together. Modern microchips are not flat. They are incredibly complex 3D structures. The process of building transistors. He is just the first floor. Now, fabrication engineers must build up layer upon layer of insulating material and intricate copper wiring to connect these billions of transistors. If the transistors are the houses and offices of our microchip city, the interconnects are the roads, highways, subways, and electrical grid. In fact, in a modern high-performance chip, the speed at which signals can travel through these copper interconnects is just as big a bottleneck as the speed of the transistors themselves. This is where the entire cycle is repeated over and over again. First, a new layer of insulating dielectric material is deposited over the entire wafer. Then, photolithography and etching are used again to carve tiny trenches and holes, called vias, into this insulating layer. Now, we need to fill these trenches with a conductor. The industry switched to copper. So engineers developed a brilliant solution called the Damascene process. They deposit a thin layer of copper over the entire wafer, filling the trenches and covering everything. Then, they use that same chemical-mechanical polishing process we saw earlier to polish the entire wafer surface. This CMP step grinds away all the excess copper from the top, leaving behind only the copper that's perfectly inlaid inside the trenches. This entire sequence, deposit insulator, lithography, etch trenches, deposit copper, polish, is repeated dozens of times, building a dense, labyrinthine web of wiring that connects billions of switches into a functioning logic circuit. It is a skyscraper of computation, built one atomic layer at a time. After months of work and over 1,000 individual steps, we finally have a finished silicon wafer. It's one of the most valuable and complex objects ever made. But it's not done. A surprisingly high number of the chips on it are already broken. The final stages are wafer sort, dicing, and packaging. Wafer sort is the process of testing every single individual chip on the wafer to see if it works. The manufacturing process is so complex that defects are inevitable. The percentage of good chips on a wafer is called the yield, and it's one of the most jealously guarded secrets in the industry. The final package is also critical. It protects the fragile silicon die, provides the metal pins, and helps dissipate the immense heat. For wafer sort, the wafer is placed in a prober machine, a sophisticated probe card with hundreds of microscopic needles, descends, and makes contact with tiny electrical pads on a single die. The prober then runs a battery of tests. If the die passes, its location is marked in a digital map. If it fails, it's marked as a reject. The machine then moves to the next die. Once the map of good and bad dies is complete, the wafer is moved to a dicing station, a high-precision diamond saw, or a laser, scribes a grid across the wafer, cutting it into hundreds of individual dies. An automated system then picks up only the known good dies. Each die is mounted onto a substrate and attached using an adhesive. Then, in a process called wire bonding, incredibly thin gold or copper wires are stitched from the pads on the chip to the metal leads on the package. Finally, the entire assembly is encapsulated from a handful of sand, melted and purified into a perfect crystal, sliced into an atomically smooth wafer, patterned with the light of an artificial star, and carved with electrified gas, built up, layer by layer, into a three-dimensional city of logic. And, finally, tested, diced, and packaged. That is how billions of microchips are made. It is the most complex, precise, and, arguably, the most important manufacturing process humanity has ever invented. The transformation of a common, worthless rock into the priceless, thinking heart of our digital civilization. If this journey from sand to silicon blew your mind, subscribe to the channel for more deep dives into the technology that shapes our world.